In this video, I'm going to talk a little bit about how to estimate the strength of transitions in atoms. Now, what do I mean by strength here? Well, in a previous lecture, we introduced the concept of an Einstein A coefficient. And we showed that this Einstein A coefficient could be related to various other Einstein coefficients, such as the Einstein B coefficients, B12 and B21, which govern the absorption and stimulated emission of photons in an atom. And if you recall, we had that A21, the Einstein coefficient governing the spontaneous decay from an upper energy state to a lower energy state, is equal to 2h nu cubed over c squared times B21, which is the coefficient that governs stimulated emission, so a stimulated transition from an upper to lower energy state. We also had that the coefficients for the absorption of a photon and the coefficients for the stimulated emission of a photon were approximately equal up to these degeneracy factors for the degeneracies of the upper and lower energy states. And finally, we showed that we could express the absorption cross-section for an atom absorbing a photon as lambda squared over 8 pi times the Einstein A coefficient over a frequency width corresponding to the transition, where 1 over delta nu was related to the line profile function. So what we mean when we say estimating atomic transition strengths is basically how readily these atoms interact with photons, absorbing them, emitting them. And that in fact all of these interactions with photons boil down to a single coefficient here, the Einstein A coefficient, that describes that transition. So estimating atomic transition strengths boils down to estimating the Einstein A coefficient for that transition. So let's recall what that Einstein A coefficient is. If we had an atom with two energy states here, E1 is the lower and E2 is the higher energy state, and we put that atom into a higher energy state. Let's call these electronic transitions. So we'll put an electron in the higher energy state. Now if we put a bunch of atoms in this excited state and graph the number of atoms in the upper energy state, so the number in energy state 2 is a function of time, we'd find that the number exponentially decays, and this is because atoms spontaneously transition to lower energy states and emit photons. And the number follows an exponential decay with a half-life that's characterized by some time scale. And that half-life, that time scale over which you expect half the atoms to spontaneously decay, is related to the Einstein A coefficient. It's in fact the inverse of an Einstein A. So this means that Einstein A coefficients have units of inverse seconds. Now in another video, we examined a semi-classical model of the hydrogen atom, the Bohr atom, in which you assume that you have a proton with an electron going around it in a circular orbit. And we inject just a small amount of quantum mechanics. We say that angular momentum is quantized in this system, and after that, we could actually, just using classical physics and kind of order of magnitude derivations, we could derive a surprising amount about the hydrogen atom. And it turns out we can use the same model to estimate what the Einstein A coefficient would be for an electron in the second excited energy state compared to the ground state. And a simple way to do that, which is a simple way to estimate this lifetime, is you can estimate this as approximately the energy of the excited state divided by the rate at which energy is radiated off in a kind of classical approximation of an electron being accelerated as it orbits around the proton times. Now if you recall, in our semi-classical hydrogen atom, we derived that energies go as a Rydberg divided by n squared, where n is the excitation level of your electron. And so the energy difference between the second and first energy states is just a Rydberg, which if you recall is 13.6 electron volts, times n1, which is 1 in our case, minus n2, which is 2 in our case, so that makes 1 minus 1/4. And so the energy we're talking about for the first electronic excitation level in hydrogen is 3/4 of a Rydberg, which is the energy of the Lyman alpha transition. It's 10.2 electron volts. The new part of our derivation is estimating this power. And it turns out we can estimate this power pretty easily as Larmor radiation, which if you recall the equation for Larmor radiation, it's 2/3 E squared A squared over C cubed, where E is the charge, A is the acceleration, and C is the speed of light. So it's kind of absurdly simple to model the power radiated by the electron using this Larmor formula. But as we showed in our derivation of the Bohr atom, this absurdly simple model actually gets you pretty dang close to the right answer. And in fact, it's going to work out for us again. If you take this 10.2 eV corresponding to the energy of the excited state and divide it by the power, we plug in the acceleration from the electrical force that maintains the electron in this circular orbit, you get a time scale, it's t life, you get an answer that's within 20% or something of 2 nanoseconds. And so if you invert that, you ask what is the Einstein A corresponding to Lyman alpha, you get an answer that's 5 times 10 to the 8. And that's a good number to remember, that the strength of the Lyman alpha transition in hydrogen is 5 times 10 to the 8 inverse seconds. And the reason we want to remember that is because we can now derive some scaling relationships for Einstein A coefficients with energy. And if we have a good value to scale those off of, we can actually get other Einstein A values to a pretty good approximation, just scaling from Einstein A for Lyman alpha. So let's go to a new section here where we talk about scaling relationships. So recall that we said that the inverse of an Einstein A coefficient was a lifetime, and we could approximate that as an energy divided by a power. Now, if we wanted to find out how this scaling relationship scales with, say, the frequency of the transition, we could express E as h bar omega. Now let's see if we can get a corresponding omega, a frequency, for our power. So we already used up here that power by the Larmor formula is 2/3 e squared a squared over c cubed. And we're not going to worry about our 2/3 right now, but we'll keep our constants. So we have e squared a squared over c cubed. Now it turns out this acceleration does relate to an angular frequency, but it's not quite obvious right away. So one way you could convince yourself that that acceleration contains an angular frequency is that we said that A equals v squared over r in our derivation of the hydrogen atom, which is just the acceleration required to keep the electron moving at velocity v in a circular orbit of radius r. But in fact, the time it takes to move around a circle is 2 pi r divided by v. So v over r is an angular frequency, which means we could write this equivalently as omega squared, which would be v squared over r squared, and then we just need to multiply by an r. So following this route, we get that p, the power radiated, goes as e squared r squared omega to the 4th over c cubed. Now another cool trick that we can pull here is to look at this e squared r squared term, because a charge separated by a distance, e times r, is in fact a dipole moment. So in general, a dipole is a vector which is equal to some charge, in this case e, times some separation vector r. So you can see then that e squared r squared is actually just the dipole moment of the hydrogen atom. So p is approximately the dipole moment squared times omega to the 4th over c cubed. So when you work this all out and actually invert your Einstein A here, so we have power over energy, we get that Einstein A is approximately d squared omega cubed over h bar c cubed. And note we got the omega cubed because one of the factors of omega in our power got canceled out by the omega in the energy. And I'm going to write an omega 0 here just to help us keep track of the fact that we're talking about the frequency of a specific transition. So this is a quantized transition. This doesn't happen at any frequency. It happens at a very specific frequency, the frequency corresponding to the energy difference in this transition. So the h bar and the c cubed are just scalars here. But the big thing to remember is that the strength of a transition is going to scale quadratically with the dipole moment and as the cube of the frequency. So that's another important result. So if we wanted to do a different transition using this scaling relationship, we could estimate the Einstein A for H alpha, which if you remember is the 3-to-2 transition in hydrogen. And that energy difference is given by a Rydberg times 1 over 2 squared, so 1/4, minus 1 over 3 squared, which is 1/9. That's going to be 5/36 of a Rydberg. And that compares to Lyman alpha, which was 3/4 of a Rydberg. So omega 0 for H alpha compared to omega 0 for Lyman alpha is equal to 5/27. And the second thing we have to do is scale the dipole moment. And remember, our dipole was of order e times Bohr radius. But how does this classical radius scale with excitation state? Well, recall that the Bohr radius A0 is given by h bar squared over that's the electron times the charge squared. And so we know the angular momentum comes in units of h bar, so n must be grouped with the h bar here. So that means that the dipole moment scaling as the Bohr radius will scale is proportional to n squared. So that means that our Einstein A is probably going to have to go as n to the fourth there. So overall, we can say that our Einstein A for H alpha scales as the Einstein A of our Lyman alpha transition. And then it scales as d squared, so that's n to the fourth power. So we'll say that our transitions are characterized by the bottom energy state. So our energy state for the H alpha line ends on 2. So we'll say it's the n equals 2 state over the n equals 1 state to the fourth power. And then it also scales as omega cubed. And we said the difference in omega, ratio of omegas, is 5/27 cubed. And so you work that out and you end up with something that's really close to 5e7 inverse seconds. You compare that to the true answer of 4.4 times 10 to the 7 inverse seconds. So this way of estimating the strengths of Einstein A coefficients scales pretty well. Now let's see if we can bring this a little farther. What we just demonstrated is that we could scale Einstein A coefficients between different dipole transitions using the scaling relationship d squared omega cubed. But now let's see if we can scale our Einstein A coefficients between other types of transitions. For example, fine and hyperfine transitions are magnetic dipole transitions. So what about scaling to magnetic dipole transitions? Well, if you recall in our derivation of the classical hydrogen atom, the magnetic dipole moment of the electron was given by EH bar over 2 MEC. And similarly, the magnetic moment of the proton was given by EH bar over 2 times the mass of the proton times the speed of light. So what you might be tempted to do, and it actually works out, is to substitute the magnetic dipole in for the electrical dipole that we were using. So you could get that the ratio of an A21 for a magnetic transition, like a fine or hyperfine, compared to A21 for our electric dipoles, goes approximately as the ratio of, say, the magnetic moment of the electron compared to the strength of the dipole squared. On top of this, we'll have to always scale by omega cubed, the frequency of the transition itself. But for the same energy difference, the same omega, we would still have a difference in the strength of these transitions just because one is based off of a magnetic moment and the other is based off of a dipole moment. So when we compare these two, we just plug in that mu sub E is E H bar, and I'm going to drop constants like 2, so it's an MEC. And then we put in the dipole moment, which was E A naught, the Bohr radius squared. So just do a little more algebra here and plug in for the Bohr radius A naught equal to H bar squared over ME E squared. We plug that in, we actually get that this is E squared over H bar C squared. And it turns out that set of constants inside the parentheses there, that is the fine structure constant, alpha. That is what alpha is defined to be. It's E squared over H bar C. So for fine structure transitions, there's a factor of alpha squared that comes in the strength of the transition. So what this says is whenever we're going to transitions that involve magnetic dipoles as opposed to electrical dipoles, we need to take an alpha squared penalty. So for example, if we went to a hyperfine transition like the A21 of my favorite transition, the 21 centimeter transition, which is the spin flip transition in the ground state of hydrogen, we could scale that off of the Einstein A that we know and love of Lyman alpha. And to do that, we just need to take a penalty of alpha squared for using a magnetic dipole transition, and then we just need to scale off of omega cubed. I'm going to use wavelengths instead. The wavelength of Lyman alpha is about 120 nanometers. Wavelength of 21 centimeter is, surprise, 21 centimeters, and it scales as that cubed. So you work this out numerically, you plug in 1 over 137 for alpha, and you get the ratio of these Einstein A coefficients should be about 1 times 10 to the minus 23. So if we plug in 5 times 10 to the 8 for Lyman alpha's Einstein A, we get that we can estimate the Einstein A coefficient for 21 centimeter emission, 5 times 10 to the 8 times 1 e minus 23, and that gives us 5 times 10 to the minus 15 inverse seconds. It turns out the actual answer is 2.88 times 10 to the minus 15. So our coarse scaling across 23 orders of magnitude came out within a factor of 2, which isn't bad. And just to put this Einstein A coefficient in perspective, whereas the expected lifetime of a hydrogen atom in the n equals 2 state for Lyman alpha was about 2 nanoseconds, the inverse of 5 times 10 to the minus 15 seconds comes out to be around 10 million years. Now there are a couple other scalings that I'd like to do. So we did scaling to other electrical dipole transitions. We did scaling to magnetic dipole transitions. I want to do electrical quadrupole transitions, but before I do that, I'm going to do one more thing with our scaling to other transitions in hydrogen. So you recall we did the Balmer alpha transition here, and we said that it generally scaled as n to the 4th power times this ratio of the frequencies of H alpha to Lyman alpha cubed. But I wanted to take this to a higher level conclusion with radio recombination lines. So for radio recombination lines, these are very high n transitions where maybe you're going from the n equals 110 to the n equals 109 state. So these have very small energy differences, which is why they are radio recombination lines. And in this case, you recall that this term right here was the ratio of the energies, which scaled as 1 over n1 squared minus 1 over n2 squared. And we did this explicitly plugging in the 2 to 1 transition for Lyman alpha and the 3 to 2 transition for Balmer alpha. But for radio recombination lines, these are going to be very close to one another. And in fact, this difference between quadratics is going to be proportional to 1 over n cubed. That's just the derivative of 1 over n squared. So in this case, we get that A21 for radio recombination lines is going to be proportional to, we have an n to the 4th for the change in the dipole moment here, and then we have a n to the minus 3 to the 3rd, so n to the minus 9 for the change in the energy, which turns into the change in the frequency. So in general, radio recombination lines scale as n to the minus 5. So that's a very steep dependence on n. All right, so that was radio recombination lines, which was just a special case of being able to take a derivative of the 1 over n squared dependence of the frequency in hydrogen. So the last thing I wanted to do was quadrupole strengths. So in contrast to a dipole where you have a positive and a negative charge separated by some distance, a quadrupole is a pair of dipoles. So you have 2 dipoles associated with one another. And we've worked out, whereas the electric field of a monopole scales as charge over distance squared, whereas the electric field of a dipole has an additional factor of the separation between charges over the radius you are from the dipole. So similarly, for a quadrupole, you'd expect the electric field to go as q over r squared times the separation between charges in the quadrupole over radius squared. Now, why are we looking at the electric field here? Well, if you recall our derivation of Larmor radiation, it's kinks in the electric field that are actually carrying off the power that is Larmor radiation. And therefore, the power radiated by a quadrupole compared to the power radiated by a dipole is going to scale as the strength of the electric fields squared. So for a quadrupole, you get an S over R squared for the electric field, and then squared again for power, so that's to the 4th power, as compared to the dipole where you get an S over R squared. So we're working out the ratio of powers radiated for a quadrupole versus a dipole, and we've got an expression that depends on the charge separation and the radius we're evaluating it at. Now the reason that we're comparing these 2 different powers is we want to compare for different transitions the total amount of power radiated with a quadrupole versus a dipole. But to compare 2 different transitions, we need to evaluate these transitions at equivalent distances from their radiator, equivalent R's. It turns out when you're radiating through electromagnetic radiation, everything scales in units of wavelength. So if we want to compare the total power radiated off by a quadrupole versus a dipole, when we say radius, we really mean radius in units of wavelength. And so for an equivalent physical radius, we'll find that the ratio of these powers is the charge separation over wavelength squared. Now remember, an Einstein A we estimated as a power over an energy to get units of inverse time. Therefore, the Einstein A of a quadrupole compared to the Einstein A of a dipole will similarly scale as s over lambda squared. So let's estimate numerically the Einstein A of a quadrupole transition. So to make a quadrupole, we need two sets of dipoles. And it turns out molecular hydrogen, H2, which is two hydrogen atoms bound together, is a quadrupole. And the first rotational transition of H2 has a wavelength of 28 micrometers. So we can estimate A21 for our H2 molecule. So if you go to work this out numerically, you get the Einstein A for this first rotational transition in H2 is equal to the Einstein A for Lyman alpha, which is 5 times 10 to the 8, as we know, times the charge separation. And here we'll just have to estimate this as something like a Bohr radius. So 0.5 times 10 to the minus 8 centimeters divided by 28 micrometers. So that's 28 e to the minus 4 centimeters squared. So that's our quadrupole to dipole scaling times, and now we just need to do the frequency scaling, frequency cubed. We'll do again in wavelengths as 120 e to the minus 7 centimeters for Lyman alpha divided by 28 e minus 4 centimeters for our rotational transition in hydrogen cubed. You work all that out and you get about 1 e minus 10. It turns out the actual value here is 3e minus 11. So in this case, we missed by maybe a factor of 3, but to order of magnitude, that's still a pretty good approximation, and isn't bad considering that we totally made up a charge separation of an angstrom inside of a quadratic scaling. So that's all we're going to do for estimating the strengths of transitions today. We have Einstein A coefficients that describe the strength of transitions, and we described how these Einstein A's could be scaled from an order of magnitude estimate of Lyman alpha, where we got that the Einstein A for Lyman alpha was 5 times 10 to the 8 in CGS units. And then we scaled that to various different transitions, both to other dipole transitions, where we found that it scaled as omega cubed. We scaled it to magnetic dipole transitions, where we saw that we picked up a factor of the fine structure constant alpha squared. We scaled to other transitions like radial recombination lines in hydrogen. And then finally, we scaled to do quadrupole transitions like those in molecular hydrogen. And we found through all of these coarse scalings that to order of magnitude, we could estimate our Einstein A's fairly well using some simple scaling relationships.